The National Electrical Code, or NEC, Article 250.30, A1, states that a service entrance is required to have a disconnecting means and overcurrent protection for all ungrounded conductors. When a distributed generator, or DG, is connected on the load side of the feeder breaker in the original service entrance equipment, it's not considered part of the service entrance. Consequently, it lacks its own disconnecting means or overcurrent protection. For effective ground fault protection, the return current from the DG must be able to flow through the service entrance grounding system. This is typically achieved by bonding the DG grounding electrode system to the service entrance grounding electrode system. To guarantee adequate ground fault protection, installing a service entrance for the DG is crucial. This service entrance would offer the necessary disconnecting means and overcurrent protection for the DG, along with the grounding electrode system for the return current. While the NEC generally discourages multiple service entrances, Article 250.31 provides an exception for emergency systems. This allows a separate service entrance for an emergency or standby system, provided it's specifically designed and approved for this purpose. It is recommended that a service entrance be installed for the DG when it's connected on the load side of the feeder breaker. This service entrance should incorporate a disconnecting means, overcurrent protection, and a grounding electrode system. The DG service entrance should be clearly labeled as an emergency or standby service. The transfer switch should be designed and approved for use with an emergency or standby system. Regular inspection and testing of the DG and its service entrance are essential to ensure proper operation. To delve deeper into the specifics of ground fault protection and distributed generator installations, let's explore the relevant sections of the National Electrical Code. We will cover the key requirements outlined in Article 250, focusing on grounding and bonding procedures. This is essential for ensuring the safe and effective operation of your system. Firstly, we will look at Article 250.20, which addresses the general requirements for grounding of electrical systems. It emphasizes the importance of grounding to limit voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines, and to stabilize voltage to earth during normal operation. Secondly, consider Article 250.24, which discusses grounding service-supplied alternating current systems. This section details how to properly ground the neutral conductor of a service to the earth, ensuring a low impedance path for fault currents to return to the source. Thirdly, when dealing with separately derived systems like generators, Article 250.30 is crucial. This article provides specific rules for grounding these systems, including the requirement for a grounding electrode system and bonding jumpers. Fourthly, Article 250.31 provides the exception for emergency and standby systems, allowing for a separate service entrance under specific conditions. This section emphasizes the need for the system to be designed and approved for its intended purpose, ensuring safety and reliability. Fifthly, Article 445 covers generators, including installation and wiring requirements. It addresses overcurrent protection, disconnecting means, and other safety measures to prevent damage and hazards. Sixthly, for transfer switches, refer to Article 700 for emergency systems and Article 701 for legally required standby systems, and Article 702 for optional standby systems. These articles outline the requirements for transfer equipment, ensuring a smooth and safe transition between the normal power source and the generator. Seventhly, Article 100 provides definitions of key terms like service equipment, and grounding electrode system. Understanding these definitions is essential for correctly interpreting and applying the NEC requirements. Eighthly, in addition to the NEC, local codes and regulations may have additional requirements for generator installations. It's crucial to check with your local electrical inspector or authority having jurisdiction, ORG, to ensure compliance. Ninthly, proper bonding is essential for minimizing voltage differences and providing a low impedance path for fault currents. Use appropriately sized bonding jumpers to connect all metallic enclosures, raceways, and equipment grounding conductors. Tenthly, regular maintenance and testing are critical for ensuring the reliable operation of your generator system. This includes inspecting wiring, connections, and grounding components, as well as testing the generator under load. Ground fault protection is a critical safety feature in electrical systems, designed to quickly detect and interrupt ground faults, which occur when current flows through an unintended path to ground. A ground fault can result from damaged insulation, loose connections, or other equipment failures. The purpose of ground fault protection is to minimize the risk of electrical shock, fire, and equipment damage. There are several methods for providing ground fault protection, including ground fault circuit interrupters, or GFCIs, ground fault equipment protection, or GFEP, and high resistance grounding. GFCIs are typically used in residential and commercial applications to protect people from electrical shock. They work by monitoring the current balance between a hot and neutral conductors. If there's a difference of 5 milliamps or more, the GFCI will trip, interrupting the circuit and preventing electrical shock. GFEP is commonly used in industrial and commercial applications to protect equipment from damage caused by ground faults. GFEP systems typically use a current transformer, or CT, to monitor the current flowing to ground. If the ground fault current exceeds a predetermined threshold, the system will trip, interrupting the circuit and preventing equipment damage. High resistance grounding is used in some industrial applications to limit the magnitude of ground fault currents. This can reduce the risk of arc flash and equipment damage. In a high resistance grounded system, a resistor is connected between the neutral point of the transformer or generator and ground. This resistor limits the ground fault current to a safe level. The NEC provides detailed requirements for ground fault protection in various articles, including Article 230.95 for services, Article 215.10 for feeders, and Article 517.17 for healthcare facilities. These articles specify the types of ground fault protection required, as well as the performance requirements for the protective devices. When installing a generator, it's essential to consider the impact on ground fault protection. The generator may need to be equipped with its own ground fault protection system, or the existing ground fault protection system may need to be modified to accommodate the generator. Transfer switches play a crucial role in generator systems, allowing for a seamless transition between the normal power source and the generator. There are two main types of transfer switches: manual and automatic. Manual transfer switches require a person to manually switch between the normal power source and the generator. Automatic transfer switches, or ATSs, automatically switch to the generator when the normal power source fails. ATS are commonly used in critical applications such as hospitals, data centers, and emergency response facilities. The NEC provides requirements for transfer switches in Articles 700, 701, and 702, depending on the type of system. These articles specify the requirements for transfer switch ratings, operation, and testing. When selecting a transfer switch, it's essential to consider the load requirements, the generator capacity, and the applicable codes and standards. The transfer switch must be properly sized to handle the load, and it must be compatible with the generator. It's also important to ensure that the transfer switch is listed and labeled by a recognized testing laboratory such as UL or ETL. Grounding electrode systems are a critical part of any electrical system, providing a lower impedance path for fault currents to return to the source. A grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes. The NEC provides detailed requirements for grounding electrode systems in Article 250. A grounding electrode system must be installed at the service entrance and at each separately derived system, such as a generator. The grounding electrodes must be bonded together to form a single grounding electrode system. The grounding electrode conductor must be sized according to the NEC tables based on the size of the service entrance conductors or the generator output conductors. Proper installation and maintenance of the grounding electrode system are essential for ensuring the safety and reliability of the electrical system. All connections must be tight and corrosion resistant, and the grounding electrodes must be protected from damage. Regular inspections should be performed to ensure that the grounding electrode system is in good condition. Overcurrent protection is another critical safety feature in electrical systems, designed to protect equipment and wiring from damage caused by excessive current flow. Overcurrent protection devices include fuses and circuit breakers. Fuses are one-time devices that melt when the current exceeds a predetermined level, interrupting the circuit. Circuit breakers are resettable devices that trip when the current exceeds a predetermined level, interrupting the circuit. The NEC provides detailed requirements for overcurrent protection in Article 240. Overcurrent protection devices must be selected and sized according to the ampacity of the conductors they protect. The overcurrent protection device must also have an interrupting rating sufficient to handle the available fault current at the point of installation. It's essential to coordinate overcurrent protection devices to ensure that the device closest to the fault trips first, minimizing the extent of the outage. Coordination studies can be performed to determine the appropriate settings for overcurrent protection devices. The NEC allows for certain exceptions to the general rules for overcurrent protection, such as for motor circuits and for certain types of equipment. These exceptions are intended to allow for the safe and efficient operation of the equipment. Emergency systems are electrical systems that are designed to provide power to critical loads when the normal power source fails. Emergency systems are commonly used in hospitals, data centers, emergency response facilities, and other critical applications. The NEC provides detailed requirements for emergency systems in Article 700. Emergency systems must be designed to automatically transfer to an alternate power source, such as a generator, when the normal power source fails. The emergency power source must be capable of supplying power to the emergency loads for a specified period of time. Emergency systems must be tested regularly to ensure that they are operating properly. The testing must include a full load test to verify that the system can supply the required power. The NEC also provides requirements for legally required standby systems in Article 701 and for optional standby systems in Article 702. Legally required standby systems are systems that are required by law or regulation to provide power to certain loads when the normal power source fails. Optional standby systems are systems that are installed at the option of the owner or operator to provide power to certain loads when the normal power source fails. These systems are similar to emergency systems, but they have different requirements for testing and maintenance. When designing and installing a generator system, it's essential to consider the applicable codes and standards, including the NEC, local codes, and industry standards. The codes and standards provide detailed requirements for the safe and reliable operation of the system. It's also important to work with qualified professionals such as electrical engineers and licensed electricians to ensure that the system is properly designed and installed. Qualified professionals have the knowledge and experience to ensure that the system meets all applicable requirements. Proper labeling is essential for ensuring the safety of electrical systems. The NEC requires that all electrical equipment be properly labeled with information such as voltage, amperage, and horsepower. Equipment must also be labeled with its listing and labeling information from a recognized testing laboratory. In the case of generator systems, the generator, transfer switch, and other components must be labeled with information such as the generator output, the transfer switch rating, and the grounding electrode system. Labeling helps to ensure that qualified personnel can safely operate and maintain the equipment. It also helps to prevent unqualified personnel from tampering with the equipment. Regular maintenance is essential for ensuring the reliable operation of generator systems. Maintenance activities should include inspecting wiring, connections, and grounding components, testing the generator under load, and changing the oil and filters. Maintenance should be performed according to the manufacturer's recommendations and the applicable codes and standards. A written maintenance plan should be developed and followed to ensure that all maintenance activities are performed on schedule. Proper documentation is essential for tracking maintenance activities and for troubleshooting problems. Documentation should include a record of all maintenance activities, including the date, the work performed, and the personnel who performed the work. Documentation should also include a record of any problems that were encountered and how they were resolved. Proper documentation helps to ensure that the generator system is properly maintained and that any problems are quickly resolved. Safety is always the top priority when working with electrical systems. It's essential to follow all safety precautions and to wear appropriate personal protective equipment, or PPE, such as gloves, safety glasses, and hearing protection. Always de-energize equipment before working on it and verify that it is de-energized using a voltmeter. Never work alone, and always have a qualified person nearby to assist in case of an emergency. Following these safety precautions can help to prevent electrical shock, burns, and other injuries. In addition to the technical aspects of generator systems, it's also important to consider the environmental impacts. Generators can produce emissions such as carbon monoxide, nitrogen oxides, and particulate matter. These emissions can contribute to air pollution and can have negative health effects. It's essential to select a generator that meets the applicable emission standards. It's also important to properly maintain the generator to minimize emissions. Generator noise can also be a nuisance. Generators can produce high levels of noise, which can disturb neighbors and can violate local noise ordinances. It's important to select a generator that is designed to minimize noise. It's also important to install the generator in a location that will minimize the impact of noise in the surrounding area. Generators can also pose a risk of fuel spills. Fuel spills can contaminate soil and water and can pose a fire hazard. It's important to store fuel properly and to have a spill containment plan in place. Proper fuel storage and spill containment can help to prevent environmental damage. In summary, ensuring proper ground fault protection when connecting a distributed generator on the load side of a feeder breaker requires careful attention to the NEC requirements. Installing a dedicated service entrance for the DG complete with disconnecting means, overcurrent protection, and a grounding electrode system is crucial for safety and compliance. Remember to label the DG service entrance appropriately and ensure the transfer switch is designed for emergency or standby use. Regular inspections and testing are essential to maintain the system's reliability. By adhering to these guidelines, you can ensure the safe and effective integration of distributed generation into your electrical system.